Hello, my name is Meghan Harrison, and I'm here to discuss my summer research at the Skeletal Tissue Engineering Lab with Dr. Lisa Larkin. My topic for today is the effect of aorta anchor storage conditions on muscle construct force production. Just a little background on the topic. The loss of skeletal muscle affects patients' physiological and psychological well-being. Right now, there's a need for a more effective method of tissue repair and replacement. The ability to engineer muscle constructs with force production similar to the muscle being repaired is an important aspect of this fabrication process, and the type of anchor used has some effect on the force productions generated. Soleus muscle constructs with aortic ring anchors were fabricated from tissue harvested from female rats. The aortic ring anchors varied with respect to their storage conditions. There were two groups in growth media, one at 4 degrees and one at 37 degrees, and two groups in transfer media, one at 4 degrees and one at 37 degrees. The aortic rings were tested for compliance, differences based on their storage conditions, and there were 5 samples in each storage group. Here you can see a picture of the tensile testing machine we used for our research, and in the middle the aortic rings were loaded in that well, and then on the other side you can see the aortic ring, which is stretched and compressed. The constructs were later force tested. They start out as a soleus monolayer, and then aortic rings are anchored onto the monolayer. Finally, the monolayer rolls up into a 3-dimensional construct. And 1 week after rolling up, the constructs were force tested. They were the diameter, maximum force, and specific force were also recorded at that time. With respect to aortic ring compliance, the tangential modulus was found for each sample. As you can see in the first graph, the stress-strain curve is plotted, and this is for sample 1 that was stored in transfer media at 4 degrees. Then on the other graph, the last 5 points of the extension period were linearly approximated to find the slope, and that slope equals the tangential modulus. And this process was repeated for all 20 samples among the 4 groups. The average tangential modulus was found for each of the 4 groups, and as you can see here, the one stored at 4 degrees had a lower tangential modulus than the one stored at 37 degrees. The constructs were force tested, but before so, the diameter was recorded, and they had basically the same diameter across the board. The one stored in 37 degrees in GMA had a little bit lower diameter. Then the average maximum force was recorded, and again, there was not a significant difference between the 4 groups. Finally, the specific force was measured, and this is found the maximum force over the cross-sectional area. And as you can see, the one stored in GMA in 37 degrees had the highest specific force, and this makes sense because they had the lowest diameter, so then they would have the smallest cross-sectional area and the largest specific force. Overall, there was not a significant difference between the 4 different groups of aortic rings stored at different conditions with respect to their compliance. As follows, there's also not a difference between the 4 groups with respect to their diameter, maximum force, and specific force. So in the future, we'll be storing our aortic rings for our soleus monolayers at 4 degrees in transfer media. So thank you. I hope you enjoyed my presentation.